Good morning, everybody. Welcome to another fun-filled morning of Chem 1105 with your host, me, Dr. White. Got a fun morning today. We're going to go through some exciting stuff. Game plan for today. I'm going to do chapter 4. Oops, get it fixed. Chapter 4, problem set. Then we'll continue on with one of my favorite areas, the mole. Remember, a mole is a chemist county unit, not a furry little animal that digs holes in the ground. I'll never do that again. But anyways, let's get going. But before we do that, remember, I believe a week from this Thursday is test 2. Test 2 historically is the lowest average of the semester, the hardest test. But I've had classes prove that wrong. How did I do that? Do the practice problems. So make sure you're keeping up and doing the practice problems. Speaking about practice problems, let's look at chapter 4 practice problems, which will be on test 2. All right, first one, draw the Lewis structure for the following elements. Well, how do you do that? Well, first of all, you have to find out how many valence electrons an element has, which means I forgot to do the following. All right, let me make it visible to you. Oh, it should be. Everybody see the periodic table? Thumbs up, people. Thumbs up, people. Wake up. Everybody see the periodic table? Uh-oh. All right, this is a test. Give me a thumbs up if you see the periodic table on your screen, please. Thank you. All right. Now, how do you find the valence electrons? You look at the number at the top of the column, either Roman numeral or in red, numeric, and that tells you how many valence electrons. For hydrogen, 1, and for an element, wrong thing, hold on. For an element, you put 1 dot on a side around its chemical symbol until you have 1 on each side, and then you double up. You never have more than 2 dots on a side for an element. So hydrogen has 1 dot, and it could be on either any of the 4 sides. Same thing for sodium. Calcium, 2 valence electrons, 2 dots, and there are other ways of writing it. Now, carbon has 4 valence electrons. Watch closely. Carbon, 4 valence electrons. The Lewis structure is this. Why is this one wrong? Because you don't double up until each side has a valence electron. And then you start doubling up. And this is for the elements. For molecules, it's different. And if you notice, oxygen has 6 valence electrons, so I need 6 dots, 4 on each side, and 2 sides have 2. The way I have it written is the way organic chemists usually do it. So I'm going to share some fun. And since you need a periodic table, I'm asking you to write the Lewis structure for sulfur and for bromine. And here's your periodic table. Go. Sulfur, bromine, Lewis structure. And when you're done, give me a thumbs up. Remember, you're doing the Lewis structure for sulfur and bromine. All right, let's do it. How do you do the Lewis structure? You need to find valence electrons. Sulfur, chemical symbol S. Look above, valence electrons, it has 6. Bromine, chemical symbol Br, it has 7. So let's get to work. Sulfur has 6 valence electrons, bromine 7 valence electrons. Put 1 on each side, then it doesn't matter which side you double up. I'll do it this way, and this is one way. You could have also done it this way. And there are 2 other ways I could have done it. And that's how you do sulfur. Now, bromine has 7 valence electrons. 1, 2, 3, 4. Start to double up. 5, 6, 7. So this is one way. I could have just as easily done this. 3 sides have 2 dots. 1 side has 1. There are 2 other ones I could draw. And that's how you do Lewis structures. Now, what ion does the following element form? How do you do that? Let's look at magnesium. You want to write the ion, which means you have a chemical symbol and a number that's superscript. It's either plus or minus. And how do we do that? We go look at the periodic table. and here's magnesium at 12. And it has 12 electrons, 12 protons. Atomic number tells you how many electrons and protons. What's the nearest noble gas? Because we want to gain or lose electrons that have the same number of electrons as the nearest noble gas. And you have neon 2 away, argon 6 away. Which is closer numerically? Hopefully you pick 2, which is neon. Neon has 10 electrons. So how do you do this? Well, let's take a look. And we have magnesium at 12 electrons, 12 protons. It wants to go to magnesium with 10 electrons, but you never lose protons, at least in chemical reactions. I've never done it in a reaction. And remember, each electron is a -1. Each proton is a +1. Do the math, -10 plus 12, add it up, and you get +2. You're not done yet. Draw the ion. Chemical symbol, superscript +2 is the older way, which I like, or you could have written it this way, the newer way, which I don't like, but either way would be correct on a test. And that's how you do it. And example, oxygen. Oxygen has 8 electrons, 8 protons. What's the nearest noble gas? Well, neon's 2 away, helium is 6 away, and argon is 8 away, 10 away, I'm sorry. And which is the closest numerically? And time's up, hopefully all picked neon, which has 10 electrons. So how do you determine what ion oxygen will get? Oxygen has 8 electrons, 8 protons, and it wants to go to the same number of electrons as neon, 10, but it will not lose any protons or gain any. Each electron is a -1 charge. Each proton is a +1 charge. Do the math. Add it up, and you get -2. You're not done yet. How do you show the ion? Chemical symbol, superscript, -2. Or you could have also the newer way like that. Either one is correct on test. Now, sodium loses 1 electron, and therefore it has 1 extra proton. And when there's no, when the charge is 1, we just do a plus charge. For bromine, the charge is -1, and that's how you would do it. And the question is, what is this called again? Well, let's go look. What ion does the following element form? And it's determining what ion will that element form. And as always, all questions are good questions. Thank you. And Dr. White practices what I preach. There's no such thing as a dumb question in my world. In my class, in my home, anywhere. In the hallway, if you saw me at COD, no question is ever dumb. All right, let's move on. And I would, one thing. Time out for a public service announcement from Dr. White. Don't be afraid to ask questions or have me do another problem in a problem set. We got plenty of time. I worked it out because I've taught this class once or twice, a couple of times before. So always feel free to ask questions. If you want me to do another problem, always feel free to ask that too. Now we know how ions are formed. And now the question is, what is the empirical formula, simplest formula for a molecule formed from the following ions? Well, how do you do that? What's the key behind that? And the key is, and you should know this, you should know this. Oh, it's settle time. All molecules have a net zero charge. That means all ions in a molecule, the charge has to add up to zero. Now, you can't change the charge of an ion, but you can change how many they are. And the first one I believe I had was, whoops, let's get back to black ink. Sodium plus and bromine minus. And what's the empirical formula for that? Well, this is a +1. That's what this tells us. That tells us this is a -1. And does it add up to 0? And the answer is yes. So that means there's one sodium and one bromine. How do you show that? Like this. Now, let's look at another one. Calcium +2, chloride -1. And what's the empirical formula? This is a +2. It says it right there. What's chloride ion? It's a -1. Now, students try and change these numbers. You can't. But you can change how many, because this has to equal 0, because all molecules have a net 0 charge. But I can change how many. And if I have 2 of these and 1 of those, it adds up to 0. How do we show that? 1 calcium and 2 chlorine ions. And that's how you write calcium chloride. Now, when you have a polyatomic ion, you need brackets. And let's look at magnesium +2, nitrate -1. And here, magnesium is a +2, and the nitrate, this whole polyatomic ion, is a -1. Does it add up to 0? Oh, no. Well, we have to change how many, never the charge. So if this is a +2, I want this to be a -2, so I'll put that there. So what this tells us is there's 1 magnesium and 2 nitrate. When you have a polyatomic ion more than 1, when you have a polyatomic ion more than 1, you put it in a bracket, like I just did, and subscript, you put the number, how many you have. In this case, 2. And that's how you do it. I'm going to share the fun. Why don't you write the empirical formula for the molecule that has calcium cation +2 and bicarbonate -1 anions? Just wanted to check to make sure we were recording. And we are. I hope you enjoy, if you are, seeing me in instant replay on Dr. White's Chem 1105 YouTube channel. I'm so glad I do that. I think it helps you out. I hope it does. All right. I hope everybody's done. I'll give you another 10.75 seconds. Go. 10.2, 10.4, 10.55. Time's up. What charge is on the calcium cation? +2. What charge is on the bicarbonate anion? -1. Does it add up to 0? No. So how do you get it to add up to 0? You have a +2, you need a -2, put a 2 there. How do you show this? There's 1 calcium. When there's no number there, it's the number 1. And how do you show 2 of the polyatomic ion? Bicarbonate, put it in a bracket, and that's how you do it. Oh, let's do one more of these. And I don't know why my 2 didn't stay up there. And why don't you draw or write the empirical formula for a molecule with sodium plus cations and sulfate -2 anions? Your turn. All right, let's do it. All molecules have a net 0 charge. See, it even says it on my screen, so it must be true. Oh, is that lame? All molecules have a net zero charge. Know this. And to do this, write the empirical formula. Sodium has a +1 charge. When there's no number, it's +1. Sulfate, SO4 polyatomic ion, has a -2 charge. Does this add up to 0? Because it should. It better. Well, I can't change the charge, but I can change how many. If I had 2 sodium, 2 times +1 is +2, plus -2 is 0. So how do I show that? Well, I have 2 sodium, and when there's only one of these, you don't put it in a bracket. And this is sodium sulfate. Have you ever gotten those little packets that say, do not eat this? And it comes in things like if you buy electronic equipment, like a new cell phone, or if you get optical equipment, like a pair of binoculars or a telescope. I bought both of those in my life when I was young. My parents were, I can still remember it. I was in 8th grade. They bought me this beautiful telescope. Oh, did I have fun with that, looking at the moon and the planets and the stars. Nice. But anyways, they had these little packets. Do not eat this, it says on there. What are they? They're filled with sodium sulfate, Na2SO4, that you just wrote down. And that absorbs moisture and traps it. And that's why they put it in there, to keep water away from whatever is in the package you just opened. By the way, a number of years ago in a general chemistry class, one student said, oh, when I was young, I ate one of those. I asked her, did you live? I can be silly and face-to-face just like I am on Zoom. All right, next, draw the Lewis structure for the following molecules. But before we do that, oh, I don't have it here. Oh no. Ah, here it is. Before we do that, a couple things. First of all, you should know what is an ionic bond. An ionic bond, go back and look at my slides for this chapter, is a transfer of one or more electrons from one atom or group of atoms to another atom or group of atoms. I like those hand signals, props I'm using. Fancy, aren't I? Again, ionic bond is transfer one or more electrons from one atom or group of atoms to another atom or group of atoms. Covalent bond. Oh, getting all choked up over this stuff. It's exciting. Covalent bond. It's a transfer, not transfer, it's a sharing, and I do this in a classroom, of pairs of electrons between two atoms. Sharing pairs of electrons between two atoms. Remember, a pair means two. And when it comes to covalent bonds, there are 3 types you should know. I hope I didn't offend anybody by pointing, but you should know. And name the 3 types of single bonds, covalent bonds, I should say, single bond, double bond, triple bond. And if we were face to face, I'd be writing this right now on the whiteboard. And the first type of covalent bond is a single bond. And how many pairs of electrons does it have? One, which is two total electrons with one pair. The next one is a double bond. That's awful B. I can do that on a whiteboard in a classroom too. That's better. And that has two pairs of electrons. And the third type is a triple bond. And that has three pairs. Everybody get the message? You should know, single bond, one pair of electrons. Double bond, two pair of electrons. Triple bond, three pairs of electrons. All right, everybody together with Dr. White. The first type of covalent bond is, everyone, single bond, yes, louder. The second type, double bond. And the third type, triple bond. And you should know, single bond has one pair of electrons, double bond has two pair of electrons, and triple bond has three pair of electrons. Time for warning, warning, really bad humor. And they're no relationship to James Bond, 007. Sean Connery was the best James Bond. The rest of them, even though Pierce Brosnan was good, but Sean Connery was the best James Bond. If you haven't seen Dr. No, Goldfinger, or From Russia with Love, or Thunderball, boy, you're missing it. I saw each one of those when they first came out. I was in high school. You can tell I'm a James Bond freak. All right, now let's go back to the question. Draw the Lewis structure for a molecule. How do you do that? You need to determine the valence electrons for each element, and then they share electrons, so each element has an octet, 8 total, including shared electrons around it. The one exception is hydrogen. Its octet is 2. So if we look at HCl, hydrogen has 1 valence electron, chlorine 7. The hydrogen says, oh, I've got 1, you've got 1 unpaired, let's share, and they do. And the question is, don't forget the non-bonding electrons around chlorine when you do the valence Lewis structure for a molecule. And this is slightly different than for an element. Now, what kind of bond exists between hydrogen and chlorine in HCl, hydrochloric acid? And the answer is 1 pair of electrons being shared, single bond. And if we look at ammonia, I'm going to let you do that one. Don't look. And the question is, draw the Lewis structure for ammonia, NH3. I will tell you, and you can find this out, nitrogen has 5 valence electrons, hydrogen 1. I'll give you a big hint, nitrogen is in the center. And it's your turn. Draw the Lewis structure for ammonia. 3 points each. right, let's get going because I'll have you try another one because I'm in the sharing mood today and it helps. All right, nitrogen has 5 valence electrons. Hydrogen has 1 of them. And the hydrogen says there are 3 of them. I have an unpaired electron, you have, let's share. And it does. And the other ones do the same thing. And the question is, what kind of chemical covalent bond exists between the nitrogen and hydrogen and ammonia? And the answer is a single bond, 1 pair of electrons. All right, let's try something a little different. Right now, as you're inhaling oxygen. That's keeping you alive. Don't forget, I'm a chemical doctor, not a medical doctor, but at least I know that. And the question is, draw the Lewis structure for oxygen gas, O2. How do you do that? Well, each oxygen has 6 valence electrons, which you look up on the periodic table. We did that earlier. And here I have my 2 oxygen atoms. Each one has 6 valence electrons. Now this stuff and what I'm doing here, you don't have to write on the test, but it helps you visualize. This oxygen says, I have 1, 2 unpaired electrons. You have 1, 2 unpaired electrons. Let's share. The non-bonding electrons are still there. So that's why I'm drawing in. They come along for the ride. And we have 2 pairs of electrons, 1, 2. And what kind of bond exists between the oxygen atoms and oxygen gas, O2, that's keeping you alive right now? A double bond. 1 pair of electrons, single bond, 2 pair of electrons, double bond, 3 pair electron, triple bond. And I'm going to let you try one. Draw the Lewis structure for nitrogen gas. And 2, as you're inhaling right now, the air you're breathing is approximately 80% nitrogen gas, N2, and 20% oxygen, O2. Draw the Lewis structure for nitrogen, N2 gas. And a quick commercial from Dr. White. I'm enjoying my blueberry tea from the Republic of Tea. I already had my vanilla almond cup earlier. Those are my 2 favorite. Water from my kitchen sink. I refill those bottles for a while and then I throw them out. Oh, Rain, thank you. Do I have time? Yeah, I have time. Well, maybe after the break. Rain, remind me to tell you my tea story where I almost got in big trouble at one company I was at because of tea. All right, let's do this. How do you do this? How do you draw the Lewis structure for nitrogen gas, N2? Well, each, and you would have looked on the periodic table and see each nitrogen has 5 valence electrons. And this nitrogen says, I've got 3 electrons unpaired, and you've got 3 electrons unpaired. Let's share. The non-bonding electrons, those not involved in a bond, are still there. And 3 times 3 each is 3 pairs. And that's a triple bond. So if you're going to a party tonight to watch the next game of the Stanley Cup playoffs, I believe they're tonight, between Montreal and Tampa. I'm pulling for Montreal, even though they're in a deep hole. I don't think they'll do it, but they got this far, which is quite amazing to begin with. Blackhawks have been out of it for a couple of years now, unfortunately. I'd be pulling for them. But if you're at a party and you see somebody breathing, you can say, you know, the nitrogen in the air you're breathing has a triple bond, and the oxygen you're breathing has a double bond. And you'll lose a friend or get kicked out of a party because people do not want to hear chemistry at a party. All right, now, let's look at H. This is a molecule with a polyatomic ion, hydroxide OH. Now, if you look at the periodic table, listen carefully. Except for hydrogen, all elements in the first column, the alkali metals, and all elements in the second column, the alkaline earth metals, always form cations. I've yet to, and I've been saying this for years, I've been asking other chemists, do you know of an exception? There isn't one. Nobody's found one. All alkali metals form a +1 ion. All alkaline earth metals form a +2 metal. Don't worry if your Wi-Fi is bad. Life happens. This is high-tech class. Remember, if you have to leave the class for any reason, life happens. And if we were face-to-face, somebody could get a call, God forbid, but they have to go somewhere because of some reason. Go, get going, I would say. And the good news about my class is if you miss anything, it'll be on the YouTube later tonight. So you can always pick it up today or tomorrow. But anyways, let's get back. I'm going to go a couple minutes. Well, I think I might get done. All alkali metals form a +1 ion. We learned that. You can figure it out on your own. And all alkaline earth metals form a +2. So what does that mean? Draw the Lewis structure for sodium hydroxide. And this is an important base or molecule in the United States for manufacturing many things, including, how many of you have heard of lye soap? The old name for this was lye. Now it's sodium hydroxide. This will never be on a test. But notice you have a sodium, and sodium forms a +1 cation. But oxygen has 6 valence electrons, hydrogen 1 valence electron, and the oxygen and hydrogen say, let's share an electron. And +6 more. Notice hydrogen has its octet. Uh-oh, what's wrong here? Oxygen only has 1, 2, 3, 4, 5, 6, 7. But where did the electron that the sodium have leave to give it a plus charge? It went here. And now The hydroxide has an extra electron and it has a negative charge, and this is how you draw it. Remember, all alkali metals and all alkaline earth metals have a net zero charge. And we're going to go a couple minutes late. You'll still get your break, but I want to get this in. Your turn. Draw the Lewis structure for lithium hydroxide. Remember, oxygen has 6 valence electrons. Hydrogen has 1 valence electron. And let's look at the periodic table. Lithium is an alkali metal. What ion does it form? Same as sodium. While you're doing that, I'm going to look out in the real world. That's not good. All right, let's do this one. Now, lithium hydroxide, lithium is an alkali metal. Let's see if I'm telling you the truth. And the answer is I am. And all the elements in the first column, except for hydrogen, always form a +1 cation. You can figure it out or you can memorize it. So immediately we have this. Now, oxygen has 6 valence electrons, hydrogen has 1, and they say, let's share. But where did the electron that left lithium go? It goes here. So now this has an extra one, and that's how you do Lewis structure with polyatomic ions. And if you look at right above 5, I, sodium cyanide, you should be able to do this on your own. I'm not going to do it now, but if you want tomorrow or Monday, if you're having a problem with it, ask in class and I'll do it. But sodium is a plus charge because it always forms a +1 cation. Then you have what's called the cyanide anion. And remember, carbon has 4 valence electrons, nitrogen 5. And I'll let you figure that out on your own. Now, this chapter 4 problem set, if you haven't done it on your own, it's easy watching me do it. Remember the bicycle and the Blu-ray I said I would give you the first day if you didn't know how to ride a bicycle? The first time you got on a bicycle, you fall off. Do these on your own. That will help you do good on tests too. If you haven't done them, get to work. That's fatherly advice from me, Dr. White. And you should know all molecules have a net zero charge. And what are the 3 covalent bonds? First one, single bond, it has one pair of electrons. Second one, double bond, 2 pair. Third type, triple bond, 3 pair. Again, single bond, 1 pair. Double bond, 2 pair. Triple bond, 3 pair. And it's time for a break. I'm going to get up and stretch for a little while, and I'll see you in 5 minutes. Please come back at 10 o'clock. That's when the big hand is on to 12 and the little hand is on to 10. For those who have analog watches, for those with digital watches, 10:00. See you in 5. time to get back to work. All right. Any questions about chapter 4 before I move on? Looking at my chat down there. Looking at my speakers there. That's going to make, I can look at the sound. No, I can't. All right, let's move on back to chapter 5, part 1, which will be on test number 2, a week from this Thursday. And let's talk about the mole. Remember, the mole is a counting unit chemists use. 1 mole of an element equals Avogadro's number. 1 mole of a compound equals Avogadro's number of molecules for an element its atoms. Now, last week, I talked about molar mass, also known as molecular weight, which I will use. I don't use molar mass. And I abbreviated a lot, MW, molecular weight. And the molecular weight is the sum of all atomic masses of the atoms, and it's in its molar mass or in its formula. And we went through examples like water, 2 hydrogen, 1 oxygen, and ammonia and sodium hydroxide. Remember, for my class, and I've got to open it up because I'll need it again. For my class, when calculating molecular weights, use atomic weights, the number underneath the symbol on the periodic table, to 3 significant figures. So carbon on this periodic table, 12.011, round that off to 3 significant figures, 12.0. Oxygen, 15.999, round that off to 3 significant figures, 16.0. And let's do one more. Hydrogen, 1.001. That would be 1.01 to 3 significant figures. You should know how to do that. And based on that, you will get a molecular weight. Let's do one real quick. Actually, real slow. Now I'm going to abbreviate on a test. I'd put molecular weight of, let's do sodium hydroxide. I don't know if I did that last time. So how do you get the molecular weight of sodium hydroxide? It's the sum of all atomic weights. 1 sodium, 1 oxygen, 1 hydrogen. You look at the periodic table, and these are, I know by heart, because I work with them enough. Sodium to 3 significant figures, 23.0. Oxygen to 3 significant figures, 16.0. And hydrogen to 3 significant figures, since there's only 1, I don't have to multiply. There are more than 1, I'd have to multiply the atomic weight by the number there is. And you add this up, and you get this. 40.01. Now, remember, when you're adding, you get the same number of significant figures to the right of the decimal as the number that has the fewest. This has 1, 1, 2. Therefore, this should have 1. Keep the 0, use this to round off. It's 4 or less. So the correct answer for the molecular weight of sodium hydroxide is 40.0. And that's how you do that. Now, why need the molecular weight? All right, let's talk about molar mass, element molar mass and molecular molar mass, and I'll come up with a better name on the next slide. And that's the quantity in grams of an element that equals the atomic weight for the element. So 1 mole of an element equals its, and I'm going to abbreviate, atomic weight in grams. So what's 1 mole of silver? Well, let's find out. Silver, Ag, the atomic weight is equal to 1 mole of silver, the 3 significant figures, that'd be 108. If I ask, what about aluminum? Now, this is a little tricky. Al, round that off, the atomic weight to 3 significant figures, and that'd be 27.0. And let's do one more. Oh, let's go to the high rent district. What's 1 mole of gold weigh in grams? Time's up. Look at the atomic weight, and that's what 1 mole weighs. And that's the 3 significant figures, 197. And you should practice rounding off the various 37 elements I asked you to learn on the periodic table. If you're having a problem, don't forget tonight, my office hours, which I've changed the hours, are from 5 to 6, Monday and Wednesday night on Zoom. And also, if you need be, I'll stay after on a lab day. Now, what does the molecular molar mass mean? That's the quantity in grams of the formula mass, which is also known as the molecular weight of a molecule equals the formula mass. And what that really means is 1 mole of a compound equals the molecular weight. I promised I wouldn't write. So this is, you should really know both of these. Or better yet, know how to use them. One mole of a compound. Well, fill this all in red. Oh, that looks ugly. One mole of a compound equals its molecular weight in grams. And 1 mole of an element equals the atomic weight in grams. Now, good news, in the past, students had to memorize that in my class. However, now, and let me open up something. All right. Thumbs up, people. Do you see test 2 important information on your screen? Thank you. Look, this will be given to you at the end of test number 2 packet. You don't have to memorize this. And you should know these. 1 mole of an element equals Avogadro's, know how to use this, of atoms of that element. 1 mole of a compound equals Avogadro's number, 6.02 times 10 to the 23rd molecule of that compound. 1 mole of an element equals the atomic weight in grams of that element. And 1 mole of a compound equals the molecular weight of that compound. And being a nice guy I am, the molecular weight of a compound is the sum of all atomic weights. In the past, students had to memorize all this. I'm going to give it to you. Thank you, Dr. White. You're welcome. But what does this all mean? It means 1 mole equals atomic mass in grams. 1 mole equals the formula weight, which is also known as the molecular weight in grams. And the molecular weight is the sum of all atomic weights for a molecule. So 1 gram, 1 mole of silver, we already did. What's 1 mole of water in grams? Well, 1 mole water equals the molecular weight in grams. Sorry, I wrote this out for water. I'll try not to do that again. What's the molecular weight of water? Well, it's 2 hydrogen, 1 oxygen, 2 times the atomic weight of hydrogen to 3 significant figures is 101. You'd find that on the periodic table. That's the number underneath hydrogen. And for oxygen, it's 16.0. Do the math, 2.02. 1 times 16.0 is 1. By the way, 1 and 2 are exact numbers. So you end up with 3 significant figures added up, you get 18.02. Now, when you're adding, you get the same number of significant figures to the right of the decimal as the number with the fewest. This has 2, this has 1, which is lower. I hope you all picked 1. How do you round this off to the right of the decimal? Keep the 0, use the 2 to round off, because you should have 1. And the correct answer is 18.0 grams is 1 mole of water. So if I were to ask you, quick, get me 1 mole of water, you'd go to the lab and weigh out 18.0 grams. And that's the importance of this, because there's no way anybody on this planet, unless Superman's hiding, is going to figure out and count Avogadro's number of molecules of water, because that would be 1 mole also. You can't. Nobody can. Even with whatever equipment that exists on this planet now, you can't count. And even if you could, 6.02 times 10 to the 23rd would take you a whole long time to count. I don't know, years and years. But luckily we don't. Now, the importance of this is converting moles to different things. Now, I'm going to skip the elements because compounds are more important, but you should know how to do this. Let's look at these different conversions. And by the way, I should mention, are you ready? It's time once again to use your good buddy, your good friend, unit analysis. Yes, it's been my good buddy for a long time too. So let's look at the following. All right, I haven't done this in a while. Some thumbs up, people. Do you see 5 points? How many grams are 2.6, thank you, 61 moles of water. How do you do this? First of all, what are we trying to find? Grams, which is abbreviated by G, or sometimes I'll do G that way, more likely that way, grams of water. What are we given? 2.61 moles of water. And now it's time to use your good buddy, your good friend, unit analysis. This is the only thing I have to start with, because once I have this, I never have to look at this again. I have this, and if I have a conversion ratio, something over something, what units do I want to get to? Well, we figured that out. Grams of water. And now I'll use my good buddy, my good friend, unit analysis. Whatever we're trying to get to, the units goes on top of this ratio. Whatever we're trying to get rid of goes underneath. And what do we do? Well, let's write in those units. Grams of water, mole of water. And where do we get those numbers? From the concept one mole of a compound equals the molecular weight of that compound in grams. 1 mole of a compound equals the molecular weight of that in grams. And the molecular weight of that compound is the sum of all atomic weights. Oh no, we've got to figure out the molecular weight of water. And water, the molecular weight in grams of water is the sum of all atomic weights, which we just did. So I'm going to go through this real quick. And don't forget, use all atomic weights to 3 significant figures, and that makes your life easier. And that would be the molecular weight of water is 18.0 grams. And therefore, I can put in 1 mole of water is 18.0 grams. And that's where you get this ratio. And now moles of water divided by moles of water cancel out, because anything divided by itself equals the number 1, meaning it's gone. I'm left with the correct units I want. And now remember, 1 is part of a definition, therefore that's an exact number. The others are, this is 3 significant figures, and this is 3 significant figures. When you're multiplying and dividing, the answer you get should have the same number of significant figures as the number with the fewest. And now I've got my calculator. And if you're still having a problem with your calculator, come to my office hour or see me after lab, and I'll do the math. 2.61 times 18.0. And my calculator gives me this number. But I've got to round it off to 3 significant figures. I'm going to let you try first. This is a little more complex than I'm picking numbers at random, but why don't you try rounding off 4.698 to 3 significant figures? Go. All right, time's up. Keep the 4, keep the 6, keep the 9. That's my 3 significant figures. Use the 8 to round off. Is that 4 or less or 5 or higher? 5 or higher. Drop that, increase that by 1. Well, that becomes 10, or actually 0.1, which increases this by 1. So, and you replace that with a 0 because you want 3 significant figures. So 2.61 moles of water is this amount in grams. And this is so powerful to chemists like myself to be able to use this. Let's go through this again. How many grams are 2.61 moles of water? We're trying to find grams of water, we're given moles. Use your good buddy unit analysis. This is the only thing I have to start with. What units do I want to get my answer in? Well, you figured it out, grams of water, and you abbreviate grams with a G. Using your good buddy, your good friend, unit analysis, whatever goes, whatever you're trying to get to goes on top of a ratio. Whatever you're trying to get rid of goes underneath. Where do I get the numbers that go into the ratio? 1 mole of a compound equals the molecular weight of that compound in grams. 1 mole of a compound equals the molecular weight of that compound in grams. And the molecular weight of that compound is the sum of all atomic weights. And therefore, what did I do? Well, first I had to figure out the molecular weight, which we already went through, and I found for water, it's 18.0. Therefore, I know now here, 1 mole of a compound, in this case water, equals its molecular weight, which I put on top, 18.0 grams. And that's how you do it. Oh, let's do another one. All right, Dr. White's going to do a Winky Dink on you, and I haven't explained, I don't think, what Winky Dink is. After this problem, I will. And what I'd like you to do first, right here, or anywhere you want to do it, write down what are you being asked to find and what are you given. Again, write down what are you being asked to find and what are you given. Okay, time's up. We're trying to find, this really should be a small g, grams of ammonia. And on a test, I'd write out grams. And what are we given? Ammonia, NH3. How many moles of ammonia? 8.111 times 10⁻² moles of ammonia. And if I haven't told you this, I'm going to be starting to go for the Guinness Book of World Record for saying your good buddy, your good friend, unit analysis, the most times in a chemistry class in one semester. All right, so this is the only number I have to start with. If I had a ratio that I could multiply that number to, what units would I want my answer to be? Your turn. I'll give you 8.6 seconds. Go. And something I forgot to do. Now I remember. Time's up. And the answer is, I want to get grams of ammonia. Now, I'm going to let you try using my good buddy and your good buddy, unit analysis, what goes here and what goes here? What units? Time's up. Let's use our good buddy, our good friend, unit analysis. Whatever we're trying to get to answer-wise in units goes on top of the ratio. Whatever we're trying to get rid of goes underneath. So I can now go grams of ammonia, and down here I want moles of ammonia. Oops, let me. And one thing I didn't do in the last problem, but let me remind you, if you have A equals to B, like 1 mole of something equals molecular weight, there are two ratios you can always write. They're not equal, they're two separate ratios. So where do I find a relationship between moles of a compound and grams of a compound? And the answer is, ta-da, 1 mole of a compound equals the molecular weight of that compound. 1 mole of a compound equals the molecular weight of that compound, and the molecular weight of that compound is the sum of all atomic weights. The molecular weight of a compound is the sum of all atomic weights. So I know 1 mole of ammonia equals the molecular weight of ammonia. Oh, shucks. Dr. White didn't give this to us. Well, we got to calculate it. The molecular weight in grams of ammonia is the sum of all atomic weights, 1 nitrogen and 3 hydrogens. If you look on the periodic table, this is 1 times 14.0 hydrogen. You don't have to memorize this, but I know these by heart, so I use them a lot. Hydrogen is 3 times 1.00. 1 times 14.0, 14.0, 3 times 101. Add that up. 17.03. When you're adding, you get the same number of significant figures to the right of the decimal as the number you're adding that has the fewest. You never change the left side. So this has 1 significant figure. This has 2, which is lower. Hopefully you pick 1. So round this off to 1 past the decimal, keep the 0, use the 3 to round off as 4 or less. So the molecular weight of ammonia is 17.0. So I know 1 mole of ammonia equals the molecular weight in grams, which is 17.0. And now before I pick up my calculator, notice I have moles of ammonia divided by moles of ammonia. That cancels out because A divided by A equals 1. And I'm ready to do my calculation. So I'm going to pick up my calculator. I just did. Make sure it's clear. I just did. And the number my calculator gives me is this. But when you do multiplication division, remember you get the same number of significant figures as the number that has the fewest significant figures. This has 4 significant figures. You should know how to do that. This has 3 significant figures. The 1 1 mole is an exact number, which means it plays no role. Which is the lowest number? Hopefully you pick this number, 3 significant figures. And therefore, round this off to 3 significant figures. Your turn. 1.37887 times 10 to the 4th, round that off to 3 significant figures. Time's up. Put down your pencil and pen. No, I'm not. You don't have to. All right. Keep the 1. Keep the 3. Keep the 7. Those are my 3. The next number, which is an 8, I use to round off. So have 4 or less or 5 or greater, 5 or greater. That and everything else I drop. Not this part you keep. And increase the number in front by 1. And the correct answer is 1.38 times 10 to the 4th grams of ammonia. And that's how you do it. Oh, I'm going to let you try one on your, let me do this again before I let you try one. And that is, we're trying to find how many grams of ammonia we're given how many moles. Here's what we start with. We're trying to get to a unit answer in grams or of ammonia. And if we had a ratio, which we do, how do I convert moles of ammonia to grams of ammonia? I use my good buddy, my good friend, unit analysis, put what I'm trying to get to on top of the ratio, grams of ammonia, put what I'm trying to get rid of. I don't want moles of ammonia in my final answer unit-wise. Underneath, where do you get this? 1 mole of a compound equals the molecular weight in grams. In this case of ammonia, the molecular weight of ammonia is the sum of all atomic weights. And therefore, I add it up, get 17.0, 1 mole of ammonia, 17.0, do the math, round it off, and I'm done. All right, first thing we're going to do is stepwise. First thing, right here, write down what are you being asked to find and what are you given. All right, what are we being asked to find? How many grams of water? What are we given? How many moles of water we have? Now, there's only one thing we have to work with, and once we do this, we never have to look up there again. And this is the only number I have to work with, so I'm gonna start with that. Now, if you had a magic ratio, what units do you want your answer to be in? Put that there. Your turn. Time's up. What do you put there? Well, we figured it out right here. We want to get to grams of water. Now, I'm going to let you use your soon-to-be good buddy, good friend, unit analysis, figure out what units go on top and the bottom. Not numbers, just units. Everybody done figuring out what goes on top and bottom of that ratio? Remember, I'm not asking you to figure out the numbers, just what goes on top and bottom. Oh, get smaller. All right, let's take a look at what you should be doing. Use your good buddy, your good friend, unit analysis. Whatever we're trying to get to goes on top of the ratio. Whatever we're trying to get rid of, unit-wise, goes underneath the ratio or the bottom. So, grams of water and goes on top, this number here, and what we're trying to get rid of, moles of water, goes underneath. Now, where do we get those numbers? You look at important information, test number 2. In the past, I'd make students memorize this, but good news, I will be giving this to you. And 1 mole of a compound equals the molecular weight in grams of that compound. And the molecular weight of that compound is the sum of all atomic weights. And remember, use all atomic weights to 3 significant figures. Underneath, on test number 2, underneath where it says print your name and write it, it will say 2 things now. First one, like you saw in test number 1, please use proper significant figures for all calculated answers. And the new thing will be underneath that, it will say, please use 3 significant figures for all atomic weights. If you don't, I'll take off a point because you're not following directions. So make sure you follow directions. Plus, it'll make your life a lot easier and help you get a higher score too. So 1 mole of a compound equals its molecular weight in grams. Well, what's the molecular weight of water? Well, we just did it, so I'm going to do this super fast. So fast, I even made a mistake. And the molecular weight of water in grams is the sum of the atomic weights is 18.0. Now, before I go any further, do my units end up in the right units? Well, moles of water divided by moles of water cancel out because anything divided by itself equals the number 1, and I'm left with grams of water. Yay, I can pick up my calculator now. Clear it. And my calculator gives me this number, 7.123. I'm looking at the wrong number. Must be, I can't read the calculator screen Wednesday. And this is what the calculator, but this has 4 significant figures. This is an exact number, and this is 3 significant figures. Our answer should have 3 significant figures. And I'm going to let you round that off to 3 significant figures. I'll give you 6 seconds, 2 times 3. Five 5.2, 5.3, 5.6, 5.72. Time's up. How do you round this off to 3 significant figures? Keep the 1, keep the 2, keep the 8. Use the 2 to round off. Is that 4 or less or 5 or higher? It's 4 or less. So I'm going to drop all this, so including the 2, and it's 1.28 times 10 squared grams of water. So if I needed these many moles of water, I'd weigh out this amount of water. And that's the power of 1 mole of a compound equals its molecular weight, and the molecular weight is the sum of all atomic weights. Now, personal thing, I have been using atomic weights, 3 significant figures, for a long time. And I've used that in calculations, rounding off the way I have, where I'm going to show you some where calculations I've done up to about $200,000 in chemicals is on the line. If I do it wrong, I've just wasted $200,000 of a company's money. You do that, you get fired like that. It's never happened. And therefore, it works to use that, the 3 significant figures. I've done it. Also, do it on the test. Not the president. 2 more and it will stop. 1 more. Oh, I counted wrong. All right. Well, with that, I'm going to give you a little longer break. Why don't you come back at 10:50 and we'll continue on with our adventure with moles. I'm going to be teaching you something very powerful, really powerful. So I'll see you at 10:50 about, I think it's almost 6 minutes. Oh, am I being nice? I'm giving you an extra 60-second break. See you in 10:50. Oh no, I'm running late. Not really. Time to get going. All right. First of all, we're going to move on. What I just taught you, we will come back and do again the practice problems and maybe something else, maybe tomorrow if we have time or next week for test 2. Remember, this is material on test 2. Before we go on, there's just a little something I thought I'd show you. This won't be on a test. It's not the very best one, but it will do. Let's move me over here. All right, everybody see on the right upper part of your screen where it says home polar tank? Thumbs up, people. Thank you. Now, this is called the tank wagon. What they don't have is, oh, they have one down here with the truck in front. And these are used to deliver chemicals that are liquids at room temperature or slightly heated because they are insulated. And this is called a tank wagon. And tank wagons are standardized. They're 40,000 pounds, 5,000 gallons. How do I know that? Because I know the density of chemicals in there. It's approximately, like I said, it's 40,000 pounds, approximately 5,000 gallons. Now, if you ever seen one at a gas station, they're delivering, assuming they're filling the tanks completely up underneath the gas station, 40,000 pounds, 8,000 gallons, 5,000 gallons, 40,000 pounds of chemical gasoline. Now, the ones you see for the gas stations has 4 compartments for the different types of gas. But in the chemical industry, we mainly use this one compartment and you fill it up. Now, what I'm going to be teaching you, hold on, I'm thirsty. This is thirsty work. I will be teaching you something now that's one of the most powerful concepts I know in chemistry, period. And it allowed me to, when I worked in the chemical industry, and I still do consulting, when I'm asked to write a procedure for a chemical plant, I've written procedures where we use up to about 160, 180,000 pounds in one reaction. That's 4 or a little more than 4.5 of those. That's big time chemistry. It's fun too. But what I'm going to be teaching you, I have used that to determine how much of each chemicals are used. And it's fun when you're at that scale. Later in the semester, I'll be showing you the inside of a chemical plant. I'll cut it out of the video, so I'll make sure you come when I do that. I'll be a special surprise later in the semester. All right, we've done some of these conversions, and we'll come back to them. Uh-oh, hold on 1 second. All right. I don't know why it happens, but Word hangs up. So I've got so many things running on this computer and I got to close it down and reopen it. All right, let's continue on. All right, thumbs up, people. Do you see calculations using molar mass, which we just went through? Thank you, Ashley. All right, now we did some examples on my whiteboard. Let's move on. Now, when we're talking about moles, important concept in weights is called conservation of mass. And the law of conservation of mass in any chemical reaction, the total amount of matter in the reactants is equal to the total amount. The dreaded T virus got my T right there. The amount of matter in the products. I will never ask you this, but this is an important concept. Whatever you start with total in grams, you end up with that in grams. And how does that affect us? Using this. This is the most powerful thing I know in all of chemistry. Calculating moles using mole-mole factor. The coefficients in a balanced chemical equation give the numerical relationship among formula units used up or produced in a chemical equation. A better way of saying that is the coefficients in an equation, balanced chemical equation, give the fixed molar ratios between substances consumed, reactants, and or produced in a products in a chemical reaction. What does that mean? What is this so powerful? Why? Well, let's find out. All right, let's look at the following balanced chemical equation. And let me make this a little larger. All right, thumbs up, people. Everybody see 2 hydrogen plus an oxygen going, thank you. All right, what this means is really the coefficient, the number in front. And when there's no number in front, the number is 1. So what this really means is 2 moles of hydrogen react with 1 mole of oxygen to give 2 moles of water. Again, 2 moles of hydrogen. The number in front is the molar quantity. Now, you can say molecules or atoms, but now you know that's 2 moles of hydrogen react with 1 mole of oxygen to give 2 moles of water. And this is true for any balanced chemical equation. The coefficient, the number in front, tells you how many moles of each reactant or product are used in or made in that chemical reaction. So what does that mean? I'm writing the problem out. All right, if you react 8.73 moles of oxygen with an excess of hydrogen, then how many moles of water are produced? Well, what do? First of all, you figure out what are you being asked to make or find, calculate. How many moles of water? What are you given? You're given 8.73 moles of oxygen react. Now, whenever you see an excess of a compound, that means you don't have to consider it. What this means is 8.73 moles of oxygen will react with all the hydrogen needed to react all of this oxygen. You will also be given a balanced chemical equation. Because you can't do the problem without it. So you'll be given this balanced chemical equation, and we figured out we're trying to find this, and we're given also this. So what do? You use your good buddy, your good friend, unit analysis. It's been my good buddy for a long, long time. And how do you do that? You come here and say, this is the only number I have. If I had a ratio, what units do I want my answer to be? And the answer is moles of water. And now I'm going to use my good buddy, my good friend, unit analysis. Let me get this thing out of the way. Hold on. Whatever I'm trying to get to, the units go on top. Whatever I'm trying to get to, the units go underneath. So I have on top moles, water. I'm about to sneeze, so excuse me. Oh, that was a slow evolving sneeze. I feel better already. Excuse me. All right. Whatever you're trying to get to goes on top, units of the ratio. Whatever you're trying to get rid of, moles of oxygen, go underneath. And where do I get these numbers? From the balanced chemical equation. For every 1 mole of oxygen, how many moles of water do I make? And it tells me 2. For every 1 mole of oxygen, from right up here, remember when there's no number, it's the number 1, I make 2 moles of oxygen. These are exact numbers. Therefore, this is 3 significant figures. My answer better be 3 significant figures. So now, before I pick up my calculator, notice here I have moles of oxygen divided by moles of oxygen, means it cancels out because anything divided by itself is number 1, meaning it's gone. And I'm left with the right units, moles of water. Yay. And now I can pick up my calculator, clear it. 8.73 times 2 divided by 1. And my calculator gives me the number 1.746 times 10 to the first power. And if you also, you might have gotten 17.46, but it's easier for you guys to round off with this. This is 3 significant figures. Remember, test 2 like 1, give all calculated answers of proper significant figures, multiplication division, which this is, you get the same number of significant figures as the number that you're multiplying, dividing that has the lowest significant figures, but you ignore exact numbers. They don't have it. role in determining significant figures of the answer. And therefore, we have 3 significant figures. Round this off to 3 significant figures. Your turn. All right, how do we round this off to 3 significant figures? Keep the 1, keep the 7, keep the 4. Use the 6 to round off. Is that 4 or less or 5 or higher? Hopefully I'll pick 5 or higher. I drop that, increase this by 1. And that's how you do it. Let's go through what I did. The question is, if you react 8.73 moles of oxygen with an excess of hydrogen, H2 is hydrogen, then how many moles of water, and hope you all know water is H2O, are made? So right here, I figure out I'm trying to find moles of water. That's why I put the question mark there. And I'm given this number, but I'm also given the balanced chemical equation. See, it even says that you'll be given that, and you will. And now, this is what I start with, because that's the only number. What units do I want to get to in my answer? And the question, you figure it out, moles of water. Then you use your good buddy, your good friend, unit analysis. Whatever you're trying to get to goes on top of the ratio. Whatever you're trying to get rid of goes underneath. Now, where do I get these 2 numbers in the ratio? Where do I get a relationship between moles of oxygen and moles of water? The balanced chemical equation, the coefficients, and if there's no number there, it's 1. 1 mole of oxygen makes 2 moles of water. 1 mole of oxygen makes 2 moles of water. We don't need it, but we might have had to use 2 moles of hydrogen make 2 moles of water, but we're not using that because, as we said, you have an excess. And now 1 mole of water, 1 mole of oxygen, 2 moles of water. These are exact numbers, do the math, and that's how you do it. Let's see if this is balanced. 6, 6, 2, 2. You will be given this. And again, the question is, and I could word it different ways. It's the same any way you look at it. And the question is, how many moles of ammonia, NH3, are produced if you react 2.057 moles of hydrogen? That's the 7. Hold on. That's the nicer 7, 2.057 moles of hydrogen with an excess of nitrogen. So right here, what I want you to do is figure out, what are you being asked to find? What are you given? Your turn right now, just do that. All right, let's take a look at this. What are you being asked to find? How many moles of ammonia? So I like to do this. What are you given? You're also given excess of nitrogen. As soon as you see excess, excuse me, of something, ignore it, because that means you got enough of that to react whatever you can react with. Uh-oh, hold on. I need to drink some water. Voice check, moles, moles, moles. Oh, it works again. Voice check, good. Now, we're also given the balanced chemical equation, which we'll need in a little while. Now, the only number I have to start with right here is this number. If I had some magic ratio, it's not magic, it's chemistry, I could multiply something times that and divide it to get my answer. What answer unit-wise do you want right there? You write it in. Oh, I forgot to teach you about Winky Dink. After this problem, somebody remind me Winky Dink. Come on, help Dr. White out. He has to figure out what goes here. You write it down your paper. Time's up. And the answer is moles of ammonia, because it's right here. We figured it out. Now it's time to use your good buddy, your good friend, and up on top and bottom, right here, just put the units. Again, help Dr. White out. I don't know what to do. Help me out. I'm doing classic Winky Dink now. I've just pulled the awesome generation gap on all of you. Right now, you're trying to figure out what units go on top and bottom of the ratio. And use your good buddy. All right, time's up. What do? Use your good buddy, your good friend unit analysis. Whatever units I'm trying to get to, go on top of the ratio. Whatever units I'm trying to get rid of, go underneath at the bottom of the ratio. And now I can write them in. I want on top mole of ammonia, NH3, and underneath I want moles of hydrogen. Now, where do you get those numbers? Hint, I'll let you try right here. What do you fill in there? Time's up. You look at the balanced chemical equation. The coefficients tell you molar ratios. This tells me for every 3 moles of hydrogen, for every 3 moles of hydrogen, how many moles of ammonia do I make? And the answer is 2. For every 3 moles of hydrogen, I make 2 moles of ammonia. And that's where you get these numbers. These units guide you to here to determine what we want to use. And now before I pick up my calculator, notice moles of hydrogen divided by moles cancel out because anything divided by itself equals the number 1. And now I know I'm in the right units. Remember, these are exact numbers. and play no role in this calculation. How many significant figures in this number? Yep, you're right, 4 significant figures. Therefore, my answer should be 4 significant figures. And note to Dr. White. And now I can pick up my calculator, clear it. Oh my goodness. The number my calculator gives me is this. Now, 10 to the 0 is 1. So if you want to leave that there, that's fine. I'm going to let you round this number off to 4 significant figures. Time's up. Keep the 1, keep the 3, keep the 7, keep the 1. Those are my 4 significant figures. Remember, anything past the decimal point is always significant. And use the 3 to round off. Is that 4 or less or 5 or higher? Hopefully I'll pick 4 or less. So that means I drop all this and I'm left with 1.371 times 10 to the 0. Remember, this is just the number 1. You could have also written on the test this. Either way, that's how many moles of ammonia. And that's how you do these. We're going to do more of these, but before I do, I promised, and I also left myself a note, Winky Dink. Let's see how good Google is. Everybody see Winky Dink or images of a little boy with a star on his head? All right. Disha, for the 4.114, I apologize, was that the one I just gave you or the previous one? If I make a math error with my calculator, let me know. Okay, did I get the right answer, Disha? Hopefully I'm pronouncing your name right. All right. All right, everybody, do you see on your, hold on, maybe you don't. Yeah, you should. Everybody see on your screen the little, all right, thank you, Ashley. This is Winky Dink. When I was a kid, it was one of the most popular shows on TV. He had a partner, I can't remember his name. And during the show, you can see these pictures of the kids writing on the TV screen. First of all, you would get this Winky Dink kit. It was real cheap. They sent you a piece of plastic and a grease pencil. And during the cartoon, you'd be told, kids, Winky Dink is stuck in the hull of the ship. Draw on a ladder. And you'd see this dotted line on the screen, and you draw on the ladder and help Winky Dink get out. And it was a fun program. By the way, see where this girl is writing on the screen over here, or this boy? My best friend at the time, Dickie Gale, forgot to put the plastic on there. And he wrote all over his parents' TV tube. This one, they were TV tubes, not LED screens like we have now. Oh, did he catch it bad? They could clean it off, but his parents were mad. But anyways, I've been doing a Winky Dink on you. Help me out, do this. All right. Now, if we had been in a lab, which you would have by now, and you've seen that in Beyond Lab Z, is there a balance that you can weigh out moles? And the answer is no. There's no balance you can weigh out moles. Really? What can you weigh out? Grams. Or on other places, pounds. I'm sticking to grams, but there's something called, we've been doing mole or grams per mole or mole grams. There's also pound moles or pound moles and gram moles I've been teaching you. And there's also kilogram moles. And I've been using what I'm going to teach you up to, largest calculation I've done was, I think, 180,000 pounds of chemicals. That's a lot. But let's look at what I'm going to teach you. We did our practice time. Now, let's look at a certain problem, real life problem. All right, everybody see 10 points on your screen? Uh-oh. Yes, you do. Thank you, my fastest thumbs up person. All right, let's look at this. 10 points. Yes, 10 big ones. How many grams of water are produced if you react 21.0 grams of water with an excess of hydrogen? So we're also given the balanced chemical equation. So what are we being asked to find? How many grams of water? What are we given? 21.0 grams of oxygen. And because you have an excess of hydrogen, you can ignore it. You're also given the balanced chemical equation right here. Now, if I were to use unit analysis, what I'm going to write down, don't you write down. Well, if I start 21.0 grams of oxygen, if I have a conversion factor, I want to get to grams of water, I'll put my grams of water on top and my grams of oxygen on bottom, because I know my good buddy, my good friend, unit analysis, showed me to do that. And now I'm stuck. Why? Ooh, it's writing on the screen when I talk. Why? Because there's nowhere to be found a ratio of grams of water to grams of oxygen. You can't find it because it doesn't exist in one step. What do I do? Good question. You look at finding moles or mass of a substance in a chemical equation. And this is really for mass calculations. Remember, mass in my class means grams. Calculations for reactions. And that's weird. know this, or I should say know how to use this. You're going to do 3 steps. Whatever you're given the mass of, you're going to convert to moles. We just did that. Next, whatever you now have converted to moles, you'll convert to the moles of your answer you want, unit-wise, of a molecule. And finally, the third step will be convert moles of whatever you just figured out in your answer to grams of that answer. And you use 1 mole of a compound equals the molecular weight of the compound. In this step 2, you use the molar ratios of a balanced chemical equation. Now, good news, I used to make students memorize this, but if you look on important information, test number 2, you'll see mass calculations for reactions, the 3 steps. Whatever you're given in weight, the mass of A, you convert to moles of A. Whatever you're now, second step, whatever you calculated the moles of A, you convert to moles of B, what you're trying to get to. I'll show you how to do this in a second, more, say 20, 30 seconds. Finally, the third step, you convert moles of B to mass of B. In the past, students have to memorize this. You will be given this important information, test 2. So let's clean up this a little, because you can't do this, can't do that, because there's no ratio. All right, so you need 3 steps. Step 1. Now there's a way some of you might have learned how to set this up with 3 ratios all at once. If you want to use that, go right ahead. I know how to do that, but I find even for me, I'll do it 3 steps separately. When you're dealing with a couple $100,000 of chemicals, you don't take chances. All right, step number 1. Moles of A, or I should say grams of A to moles of A. And what does that mean? What are we given grams of? Oxygen. So we want to go grams of oxygen to moles of oxygen. How do we do that? Well, use your good buddy, your good friend, unit analysis. This is what we have. We want to get to moles of oxygen. That's moles of whatever we're given grams of. And now I'll use my good buddy, my good friend, unit analysis. Whatever we're trying to get to goes on top. Whatever we're trying to get rid of goes underneath. And where do I get that? 1 mole of a compound equals the molecular weight, and the molecular weight of O2 is 2 oxygen, and it times 2 times the atomic weight, the 3 significant figures, and that's 32.0. 1 mole of a compound equals its molecular weight. And notice grams divided by grams of oxygen cancel, and we're left with the right unit. So now I'll pick up my calculator. And the number my calculator gives me Notice this is 3 significant figures. This is 3. I'm going to round it off to 3. That would be 6.56 times 10 to the minus 1 moles of oxygen. Are we done? No, we got to get the grams of water. Now, before I continue, there's something I should mention, which I've mentioned before. When you have multiple step calculations, there's 2 philosophies. One is you round off at each step using the rules you know how to round off. The other is you wait till the end. Dr. White is a round off at each step person. And I've done that, and calculations I've done, hundreds of thousands of dollars in companies' money rested on I did it right, and I did. By the way, I always did the following when I was dealing with that much money, like a couple 100,000, and I gave myself plenty of time. I'd do the calculations. Then 2 days later, I wouldn't look at my first calculations. I'd start fresh and do it again. And those numbers better match. They always did. Then I knew I didn't make a mistake, because if they're ever different, I made a mistake. Well, you don't have to do that because you're not doing $100,000, but still 10 points. All right, so I will calculate both rounding off at each step and rounding off at the end to get the numbers. Sometimes they're the same, sometimes they're different. And on a test, if they're different, either answer will always be correct. All right, so now I've done step 1, and step 2, if you look at the list, which I'll give you, is moles of A, which we just calculated, to moles of B. In this case, it's moles of oxygen to moles of, what are we trying to get to in terms of grams? But now we want to get to moles of water. And how do you do that? Well, you come here and say, well, we have 6.56 times 10 to the minus 1 moles of oxygen. We want to get to moles of water. And I'll use my good buddy, my good friend, unit analysis. Whatever I'm trying to get to goes on top. Whatever I'm trying to get rid of goes underneath. And where do I get a ratio of moles of oxygen to moles of water? I come up to my balanced chemical equation. Remember, this is 2 moles hydrogen. When there's no number there, it's the number 1. 1 mole of oxygen makes 2 moles of water. So for every 1 mole of oxygen, I make 2 moles of water. So I can come down here, for every 1 mole of oxygen, I make 2 moles of water. For every 1 mole of oxygen, I make 2 moles of water. Remember, these are exact numbers. And now I'll take the number I just calculated, this right here. And before I do that, moles of oxygen divided by moles of oxygen cancel out. And I'm going to multiply that number times 2 divided by 1. And my calculator gives me this answer. Which I'm going to round off to 3 significant figures. And the question is, this is step 2. Am I done? Well, I've got moles of water, but no, I'm trying to get to grams of water. So now I have to do step number 3. Whatever I'm trying to get to unit-wise, chemical-wise, which I now have moles of B, I will convert to grams of B. In this case, I have moles of water. I want to convert to grams of water. And how do I do that? Well, the only number I have is 1.31 times 10 to 0, which is 1.31 moles of water. I want to get to what's my answer? Grams of water. And I'll use my good buddy, my good friend. My hand's got a calculator, so I can't. Oh, I can. I better. I haven't. I'll use my good buddy, my good friend, unit analysis. And that tells me whatever I'm trying to get to goes on top of the ratio. Whatever units I'm trying to get rid of go underneath. This is grams of water. This is moles of water. And remember, 1 mole of a compound equals the molecular weight in grams of that compound. The molecular weight of water, 2 hydrogen, 1 oxygen. Added up, rounded off, is 18.0 grams. And now, before I pick it up, notice moles of water divided by moles of water give me grams of water, which is what I'm trying to do. So I'll multiply my answer. And I think I made a mistake before. I didn't round off properly. So let me clear this. Yeah, I think I did. 1.31 times 18. And the number my calculator gives me this is 3 significant figures. There's a 1 here. And this is 3 significant. This is the exact number. And rounding this off to 3 significant figures, 2.36 times 10 to the first grams of water. Whew. Now you know why it's 10 points. It's a lot of work. But this is one of the most important things in all of chemistry. If I look at the time, oh no, time flies fast when you're having fun with moles and grams and Dr. White. And with that, let me remind you, the lab we did yesterday, the balanced chemical equations are due tomorrow. Make sure you get your labs in on time, because a lot of you are going to start losing points and get zeros. With that, I'm going to say, Gang gesund. I'll see you tomorrow. We'll have our lab. It's already posted, or will be in an hour or two, in Blackboard. You don't need Beyond Lab Z for tomorrow's lab. And yesterday's lab, you didn't need it, so make sure you hand it in. With that, Gang gesund. I'll see you tomorrow. Be healthy, Gang gesund. And don't forget, I have my office hours tonight, 5 to 6 p.m. Bye.